Alright, chemistry class, welcome back to another video installment here, another video session, and we are going to be looking at chapter 12 where we are going to be discussing solutions. Now you may recall in the previous two chapters we were looking at different states of matter, solids, liquids, and gases, and in chapter 11 we looked solely at gases, at the different gas variables and gas laws. Here in this chapter, what we're going to be doing is we're going to be mixing solids and liquids and gases and coming up with solutions and different mixtures. So whereas before we looked at simply the properties and the similarities and the contrast between solids, liquids, and gases, now we're going to be mixing things. We're going to be mixing solids with liquids, liquids with liquids, gases with gases, or solids with solids, and we're going to be coming up with different types of mixtures, and we're coming up with different types of solutions, and we're going to be talking about some of the properties and so on. Okay, so that's where we're going in this chapter, chapter 12, talking about solutions. Okay, all right, now we are going to start with, so we'll look at solutions and mixtures. I do want you to take just a moment here and look at these two questions that are dealing with previous concepts, and these help you just to remember what we've talked about before, and also just to take a stab at some ideas to lead into today's chapter. Okay, so try to answer these two questions. Just put them in your notebook there, and then we'll move on. All right, let's look at section 12.1. So in your notes you could just put section 12.1, and we're going to talk about types of mixtures. So obviously mixtures are things that are going to interact. Remember we talked a little bit about gases that diffuse and liquids that diffuse, and they diffuse because those particles are constantly moving. Well, that's going to be the result of particles that are constantly moving, and when you interact different gases, liquids, or liquid and a gas, or solid and a liquid, they're going to end up mixing. Okay, now we love in science to kind of categorize things and look at different ways that things can be kind of defined. So we're going to talk about types of mixtures. Okay, all right, first of all, let's talk a little bit about mixtures that are either A, heterogeneous, or B, they could be homogeneous. Okay, now genus means a type, a kind, and hetero means different. All right, here genus means a type or kind, and homo would mean the same. So genus, this heterogeneous means basically there's going to be a mixture, but it's not going to be uniform. In other words, it's not going to be all identical throughout. You're going to see that there are some differences in your mixture that make some parts of the mixture a little more distinct and different, and can be obviously pulled out or even removed or separated from the rest of the mixture. Okay, whereas a homogeneous mixture basically is such that it is uniform. It's pretty much identical and the same throughout the mixture. Okay, here's the idea. A solution is another name for a homogeneous mixture of two or more substances, and that means in a single phase, meaning they're both gases, or they're all gases, or they're all liquids, or whatever. Okay, so another word for a homogeneous mixture is a solution. You need to know that. All right, a solution. Now, two types of heterogeneous would be a suspension or a colloid. All right, so homogeneous mixture, we call that a solution, and heterogeneous mixture could be either a suspension or a colloid. Now let me just give you some examples so you kind of get an idea of what we mean by these. solutions, which are homogeneous, the particle size is going to be tiny, 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 tiny. And that means that those particle sizes are so small that they're going to disperse themselves evenly throughout the mixture, the homogeneous mixture, the solution, and you're not even going to be able to detect any difference whatsoever. So they do not separate. There's not going to be any layers or separation or anything like that. You know that, like, sometimes when you mix something up and you let it stand, you'll start to see some things settle to the bottom and you'll start to see layers. All right? That's not the case with solutions. If you were to take a solution, you create a solution, you mix something up, right? And you're going to see that nothing is going to settle. Nothing's going to create layers, or there's not going to be any difference in that solution whatsoever. All right? You cannot separate the different the mixture, the solution, just by pouring it through filter paper. Everything will go through. The particles are so small of the different things you're mixing together that a filtration is not going to separate it. Okay. The other thing is, if you were to take like a flashlight or a beam of light and shine it through your mixture, it's just going to keep passing straight through. It's not going to be scattered or diffracted as a result of the particles that are in the mixture. Okay. Now that's different with colloids and suspensions. Remember, these are heterogeneous over here. Heterogeneous means, yeah, they're mixed up, but you're able to see that some parts of your mixture are different than other parts. Okay, here's what I mean by that. Imagine that I had a mixture, okay? I mixed something up in a glass, and I noticed that, let's say it's like, muddy water or something, okay? I mix up muddy water, put some dirt in there, and I mix it all up. You'll notice if I let it sit that some of those particles are going to settle to the bottom, and part of my mixture is going to be much different than another part of my mixture. It's not going to be the same throughout, okay? I'll give you some examples of different types of solutions. So here, this might be like, dirty water, or even milk. Milk is a type of heterogeneous mixture. Even though on a carton it might say it's homogenized. Homogenized meaning that the particles are broken down so that they spread out evenly throughout the milk. Okay, but really it's somewhat of a heterogeneous mixture because it has some fat and some water and the cream. If you let it sit maybe long enough, you might see some separation of the different things that are in that milk mixture. Okay, the particle size here though is small for a colloid. All right, they do not separate if you just let it stand, and you cannot separate it by filtration. But over here, a suspension is, the particle sizes are much bigger, and so you would be able to separate it by filtration, and the particles would settle out. Okay? All right. When it's talking about scattering light down here, what that's called is called the Tyndall effect, and that means if you were to have a glass of water here, and you were to take a flashlight, all right, that's my flashlight right there. If you take a flashlight and beam some light, send some light through that water, it would just pass right through, okay? But if you had particles in that glass of water, then the light is going to hit some of those particles and it's going to scatter. And as a result, you might actually see that beam, because some of it would scatter and come back to your eye there, and you'd see this beam of light that's being passed through here, and that's called the Tyndall effect, okay? So that beam, if you take a flashlight and you shine a beam of light through a mixture and you actually see it, that's because some of the light rays are being scattered and they're bouncing off particles, and some of them are coming to your eye, and you start to see that beam of light in that heterogeneous solution. Okay? Okay, so these are the different types: heterogeneous, homogeneous, and these are some of the properties of those different solutions, okay? Or different solutions, colloids, and suspensions. These are the mixtures, all right? Now, it's important for you to know that here, solutions are also homogeneous mixtures. Those mean the same thing, okay? So the example they give here, if you take a sugar cube and you put it in water, it will dissolve. That cube disappears little by little as those sugar molecules break away from each other and get surrounded by the water molecules so much that you don't see the sugar anymore. Okay? Eventually, if you have enough water, all the sugar molecules will spread out evenly throughout the water. Okay? You will not see any of the original sugar cube. It will not be visible. And you'll know that sugar's in there because if you taste it, it'll taste sweet, right? Even though you don't see the sugar. So the sugar molecules are still in there. It's just that they've pulled apart so much due to the water interacting with it and pulling and separating them. You won't see those sugar molecules anymore. Okay? We say that sugar is soluble, meaning it can dissolve. It means it dissolves in this case, water. Okay? So this idea here of something dissolving, creating solutions is very important. All right. When we talk about, let me talk a little bit more about solutions here. That's what we're doing right now. So this is part C of our notes. Let's talk about solutions and let's talk about the different things that we're mixing together. All right. So this is important to know the components of the solution. The solvent here, you should write down solvent in your notes, and that solvent is whatever is being is doing the dissolving. Let me put it that way. Okay, so the thing, or they say medium here, that dissolve the other substance. So in our example here of sugar water, the solvent would be the water. Okay, and the sugar is being dissolved, and that is called the solute. So in our example, the sugar is the solute. Okay? Now this would be for a solid being put into a liquid. All right? So when you take a solid and you put it into a liquid, if it dissolves, the solute is that solid that you are mixing and dissolving into water. The solvent is whatever liquid, in this case water, that is doing the dissolving. Okay? Here's what happens on a molecular level. This is really kind of cool, and I want you to understand this a little bit. But on a molecular level, if you were to take, now these are, in this case, this is two liquids that we're mixing. Over here, we would have a solid. So these are two liquids creating a solution. Here we have a solid and a liquid creating a solution. In this case, we have water. Here's a water molecule right there. That's your H2O. And we have another liquid, ethanol. So ethanol is being poured into the water, and here is an ethanol molecule right there. Well, water is polar. Remember, it has a positive and a negative end to the molecule. And ethanol is also polar. So they're going to be attracted to each other. The positive end of the water molecule is going to be attracted to the negative end of the ethanol, and vice versa. So all these water molecules here are going to start to surround the ethanol and separate them and pull them apart so that they're all mixed evenly. You start to see them evenly mixed throughout. Okay? So as a result, what happens is you have a uniform distribution of your ethanol. Okay, it's also because these liquid particles are constantly moving, and so they're going to, as we talked about before, diffuse. They're going to spread out and constantly move and actually take on the shape of this container right here, in this case that beaker. Okay, if you had a solid, in this case it's copper and chloride, so this is copper chloride, copper 2 chloride. This would be a solid, and we would then dump it into some water. Notice it's kind of changed colors there. So here we have some chloride ions. It's going to separate them. It's going to separate the copper and the chloride and the chlorine into ions. All right, and you're going to have a 2+ ion for the copper and a -1 for the chlorine. But these are your chlorine atoms that now are separated from the copper, and you're going to have ions as a result. Here's the copper, and these are going to be positive and negatively charged. So now the water comes around and separates those because they're attracted to them. The water, the negative end of a water molecule will be attracted to the positive ion, and the positive end of a water molecule will be attracted to the negative ion. And that's going to be basically surrounding those ions, pulling them apart from each other, surrounding them and pulling them apart such that you would never even see the large solid copper to chloride that you originally put in there. So you might see a color change, but you're not going to see the actual solid itself if it dissolves. Okay? You also could have a mixture, a solution of solids. So if you were to take silver and add some copper to it and uniformly distribute that silver and that copper, and also there looks like there's some gold in there as well, then you're going to get a type of metal, an alloy, that might have some different metals in there. Okay, instead of taking pure gold, you mix it with other things, and we might do that because gold is very malleable. It's very soft usually. It's quite soft. So if you want to strengthen your jewelry, you might put other metals in there and they'll make it a little more strong, but still give that gold sheen, that gold look. Okay. So we could have, what are we on here? DE, point E here. Different types of solutions here. We can have different phases or different states of matter mixed with each other to create different, different mixtures. Doesn't have to be a solid mixed in with a liquid. All right. So a liquid can dissolve a solid, a liquid, or a gas. You can take a solid and dissolve it in liquid. You can take a liquid and dissolve it in liquid. You can take a gas and dissolve it in liquid. For example, gas, there is oxygen dissolved in water so that the marine life and the lake life and the aquatic life can survive that needs that oxygen. Okay? So gas can dissolve in liquid. If you drink a carbonated beverage, there is gas dissolved in that beverage. You know it because when you open up the can, some of that gas comes out because you're reducing the pressure on it. Okay? All right? I mentioned the alloy already. An alloy is a solution of two or more elements that are metallically bonded, so two or more metals. Okay? All right. So I just want to make sure that you understand that solution. Now remember solutions. Remember what a solution is? Homogeneous. It's the same throughout. It is uniform. It looks identical all throughout the mixture. Okay? But you need to know that a solution can be a mixture of two solids, two liquids, two gases. Our atmosphere is a mixture of different gases. It's a homogeneous mixture of gases. It can be a solid and a liquid, a solid dissolved into a liquid. It can be a gas dissolved into a liquid, or a liquid dissolved into another liquid. Okay, so there's lots of ways we can make these solutions. All right. I already mentioned that the suspensions, the particles in a suspension are large and they sometimes will settle out. Okay, and the colloids are a little less large, but still they might cause the solution to appear different in different places. If you were to reach in and take a sample from that solution, you might get something a little bit different than if you were to take a sample from somewhere else. Okay? And then I mentioned the Tyndall effect. I wish there was a picture here, but the Tyndall effect is basically if the particles are large enough, then if you pass light through that mixture, it's going to scatter that light and you'll see the beam of light that's passing through there. Okay? These are just examples of different types of colloids. All right? I mean, you guys have used this stuff all the time. Okay? So, paints, mud, gelatin, milk, mayonnaise, shaving cream, smoke, fog, aerosol sprays, there's cheese, butter. These are all types of colloids. All right, you use them and see them all the time. These are the class of them, but basically it's showing you different common colloids. This is showing you that here a solid is in a liquid. Paint, mud, solid is in a liquid. Here's a liquid in a liquid. All right, here is gas in a liquid. There's a solid in a gas. There's liquid in a gas and a liquid in a solid. Okay? So this shows you different types of colloids. All right, and then we have here F. Let's look at F, point F here. Okay? Oops, sorry. Point F. All right? All right, an electrolyte are ionic solutions that conduct electricity. I mentioned before, if you take an ionic compound, let's take, for example, NaCl. This is common table salt. Oops, sorry, table salt. All right, common table salt. And you take that and you put it into water. Just like our example before with the copper 2 chloride, the sodium and the chloride are going to be pulled apart by the water. So you're going to have sodium and chloride, and when they come apart, remember this is an ionic compound. So they are bonded because there was a transfer of electrons. All right, so the metal gives up electrons to the non-metal. So if you pull them apart, now sodium has lost an electron, chlorine has gained an electron, so now they're ionic, they're charged particles. And the water is going to surround it because remember water is polar, so the negative end of the water is going to be attracted to the positive ion, and the positive end of the water is going to be attracted to the negative ion. So you're going to have water surrounding both of these here and creating these ions to be pulled apart. Sodium and chlorine are going to be pulled apart, and you're going to create now these ions in your water solution. That is called an electrolyte. If you look at a bottle of maybe like a Powerade or an energy drink or a Gatorade or something like that, something that says it has electrolytes in it. Well, all that means is they put in maybe some salt or some table salt, NaCl, or some other type of salt, maybe to give it a little flavor and also to put those ions in there. You need minerals in your body in order for many of the chemical reactions to occur, okay? Maybe for some of the things that our brain or our body needs to do to function, needs these electrolytes in them. So as a result, what do? We put certain salts into those drinks, and those are electrolytes. It'll say electrolytes, contains electrolytes on your power drink. Okay, look at it next time. Electrolytes are ionic solutions. Why? Because you put an ionic compound into water. Now, it will conduct electricity because it has charged particles in it. So electricity is just the transfer of electrons. So if you've got charged particles, there's going to be electricity that can flow through that charged solution, that electrolytic solution. Okay? Okay, that idea is summarized very nicely for you here. It says any soluble ionic compound. Remember, an ionic compound is a metal with a nonmetal. Okay? A metal with a nonmetal will separate into its positive and negative ions, as I showed you up here with sodium and chloride. All right? Now what's going to happen? That sodium chloride will separate into sodium cations and chloride anions. Okay? If it's not an ionic compound, like sugar is not an ionic compound. It's made up of all nonmetals. So if it's still going to dissolve in water, but if it dissolves in water, it is not going to break apart into ions. That is a non-electrolyte, and it does not conduct electricity. Okay? All right. We can test solutions and see if they are electrolytes or not. You can take a bulb that has some different uh, probes here and some electrodes, and you can dip it into, this is hooked up to like a battery or something. If this connection is going to be completed by the solution, then this bulb will be illuminated. It'll go on. So if you've got ions in your solution, then that bulb will go on because the circuit is complete, because thanks to the charged particles in your solution. Okay, here's sugar though. Sugar's not an ion. So when you put this bulb into a water solution that has sugar dissolved in it, there's no connection here. It is not going to conduct electricity because there are no charged particles in there. Here we have an acid actually. This would be HCl, and when you put HCl into water, excuse me, that is going to form ions. And so this will conduct electricity again, okay? All right, that concludes 12.1. Some of the things you need to know about different types of solutions, okay? Let's look at, now you're going to put down 12.2, and we're going to look at the solution process, okay? What do we go through in order to make a solution, all right? All right, first thing you need to know, there are several factors that affect dissolving. Things are going to dissolve, but sometimes things might dissolve very easily, or it might take a little work, or you might have to do something to speed up the dissolving process. So let's look at some of the factors that affect dissolving. Here's the first one. Number one, increasing the surface area of the solute is going to speed up. Increasing the surface area speeds up dissolving. Okay? Speeds up the dissolving. Here's what I mean. If you were to take a sugar cube, a cube of sugar, and put it into water and just sit it there, don't do anything, it will over time dissolve, but it'll take some time. Okay? If you were to take that same sugar cube and crush it into fine powder, and take that powder and put it into same amount of water at the same temperature, that crushed sugar is going to dissolve much more quickly, because you have basically broken apart that cube into smaller pieces, and now the water can get into all of that extra surface area and can interact with those sugar particles much more quickly, okay, and much more easily. So one way to speed up dissolution is the dissolving process is to increase the surface area. Basically, you turn your whatever it is, turn your solid into like a powder. Break it apart. Okay, break it apart. Dividing it into something that is smaller will increase the exposed surfaces, and therefore it'll dissolve faster. Okay? All right, another way to speed up the dissolving is to agitate the solution. Stir it. Okay? Stir the solution. That is going to speed it up. Basically what we're saying is this just makes it easier for new particles to dissolve. There has to be interaction, so it's going to make it easier for the particles to interact with the water. The water's got to get to those particles and pull them apart to dissolve them. If you stir it up, if you agitate it or shake it, it's going to help everything spread quicker. Okay? Stirring or shaking. All right, number 3, heating it up. Remember, in order for things to diffuse, mix, spread out, those particles have to move around a lot. If you heat something up, they have more energy and they're more likely to move, and as a result, to mix. Okay? You know this because if you were to take your, like a hot beverage and put sugar in there, it dissolves much more quickly than if you were to just put your sugar into a cold beverage. Okay? So the more energy that a solvent has, solvent, remember, is the one that does the dissolving. more energy they have, they will collide more with the solid that you're trying to dissolve and will be more likely to break apart that solid. And as a result, the solid will dissolve more quickly if you have warmer liquid versus a cooler liquid. Okay? All right, those are the different ways that we can increase the dissolving process. All right. Now, solubility is the term that we use if something will dissolve. Okay, solubility means that it is dissolving. Okay? Now, solubility is a measure of how well one substance dissolves into another. Okay? We can say that something is very soluble, and what that means is that a lot of it will dissolve into your solvent. Or if something is not very soluble at all, then it doesn't dissolve easily. Or things can be insoluble. It doesn't dissolve at all. Okay? So, we can actually measure that, how much of something is going to dissolve, and that is called its solubility. So we're going to actually have a measurement that helps us do that. Okay? When we take something and mix it, there is a maximum amount that can be dissolved. All right? Let me explain. If you have a solid, and let's take, for example, here I'll take a beaker. Since we're all familiar with water, right? Let's say this is water right here, okay? And I take some sugar and I pour some sugar in here. And it all dissolves. So I pour some more sugar in and it all dissolves. I can stir it, I can do whatever I need to do to get it to dissolve. But I'm not going to change the temperature, okay? Just leave the water temperature wherever it is. And I keep pouring some more sugar in. I pour in some more sugar and I realize, oh, there's a little pile of sugar down here at the bottom that is not dissolving. It doesn't matter how long it sits there. It doesn't matter how much I stir it or agitate it. The sugar now, there are sugar crystals at the bottom and they're not dissolving. I have reached a point where a maximum amount of sugar will dissolve in this quantity of water at that temperature. I have what's called saturated the solution. It's full. The water's full. It's not going to be able to dissolve anymore. A saturated solution is one that contains the maximum amount of dissolved solute. In our example, it's sugar. Okay? You won't be able to dissolve anymore. You can put more in, but you'll just increase to the pile of sugar crystals that are down here at the bottom. Okay? So once you start to see it, even one tiny little sugar crystal, if you can see it, but if you as soon as you start to see some sugar crystals that are not dissolving, you have saturated the solution. Okay? Up until that point, it is unsaturated, meaning you can still add more sugar and dissolve it. Okay? It contains less than the maximum amount. So saturated means you're at the maximum, and even if you add more sugar, you won't be able to dissolve any more. Unsaturated means you're less than the maximum amount. Okay? A supersaturated solution, if I heat this up, now these crystals will dissolve, and now I have a supersaturated solution that contains more than the maximum amount of dissolved solute normally possible. What I would do to create that is I heat this up and I dissolve all these crystals down here that wouldn't dissolve at the previous temperature, and then I cool it back down to that original temperature, and they might stay dissolved if I don't disturb it. Now I've created what is a supersaturated. More is dissolved in there than normally should be. Okay? Now, one other important point here. When you have a saturated solution, listen carefully. When you have a saturated solution, you have some crystals that will dissolve and go into the solution. Wait a second. Mr. Swanson, I thought you said that these will not dissolve. Well, some of them will dissolve, but when they do, you will have others that are in solution that will turn back into crystals. So you will have dissolving and crystallization happening at the same time at the same rate. Remember, these particles are always moving. So you're going to have water particles slamming into these crystals, sugar crystals, and maybe causing some of them to dissolve. But then it's too crowded up here. It's already full. So then some of them have to turn back into crystals. And there's going to be a continual cycle of dissolving and recrystallizing at the same rate. So the rate of dissolving is going to equal the rate at which they are crystallizing. Okay? And as a result, you have reached what is called equilibrium. We talked about equilibrium before, all right? But this is solution equilibrium. And that happens when it is saturated. Okay? So dissolving and crystallizing happen at the same rate. Every time something dissolves, something's going to crystallize. Something else is going to crystallize. And you will not change how much you can dissolve there. This pile will stay the same amount, even though some are dissolving, others are going to be added to it by crystallizing. Okay? And so solution equilibrium is occurring when you have a saturated solution. Okay? All right, so notice here, this is showing you that you can add more and more. This line here is showing you that the mass of what you're adding, to water, and this is at 20 degrees here. This is the mass of grams dissolved. Okay, so you'll notice here that we're adding a certain amount, and as we add it, all of it is going to dissolve. So if I add 20 of it gets dissolved. This is how much I add. This is how much actually dissolves. All right? So I keep adding this solid, whatever that solid is. In this case, you know, they give us the formula of it. But if I add 40, how much will dissolve? Yep, all 40 will dissolve. But I'm going to get to a point where if I add a certain amount, oh, it's going to max out. Look right here. See the line went flat? It maxed out. Where did it max out? Right here at 46.4. If you were to add exactly 46.4, all of it will dissolve. Exactly 46.4 grams of this solid will dissolve in water. If you were to add even a fractional amount above that, a tiny amount above that, you will have some of that tiny amount that you added above this number will not dissolve. You've saturated the solution. So if I try to add 60 right here, I add 60, nope, only 46.4 grams will dissolve. That means the remaining amount will just remain as a solid at the bottom of the beaker and will not dissolve. Okay? This number right here is called the solid solubility. How much per 100 grams of water dissolved? Okay? We'll talk about that in a little bit. So saturated versus unsaturated. You have to understand that, and you have to understand supersaturated. Okay? These are just showing you some different solubilities for different solids as it relates to the temperature. Notice here, I'll just point out one quick thing, that as the temperature increases, normally you're able to add more and more and more of a particular solid in 100 grams of water. Okay? This number is going up as the temperature is going up. You can dissolve more and more and more if you have a higher temperature. Okay? If the water is hotter. There are some exceptions, but for the most part, it increases. There are some that decrease. All right, so what do we mean by solubility here then? So make this another point in your notes. Solubility is actually something we can measure. It's something that we can get a value for. The solubility of a substance is the amount of that substance, usually in grams, required to form a saturated solution. It's the max amount. The max amount that can be dissolved in what? A certain amount of the solvent at a given temperature. So for water, we often say it's per 100 grams of water. All right, if water is our solvent, we find out how much of a solid, in this case 46.4, how much of a solid can be dissolved in 100 grams of water? And that is that particular solid's solubility level. Okay? So solubility is usually given in grams of solute per 100 grams of the solvent. So it'd be 46.4 grams per 100 grams of water. And that's the solubility of the whatever the solid was up here in our graph right here. Okay, that was 46.4. Okay. Now we've been talking a lot about dissolving things and mixing things. Here is a very important concept that you must know. How are we going to know if certain things dissolve? Well, you can try, right? You can just pour it in there or put it in there and see if they dissolve. But there's also a little very important theme or idea or phrase that you need to remember to help you know if something will dissolve. And here it is. Like dissolves like. What does that mean? It means things that are similar as far as their polarity will dissolve in each other. Okay? Let me explain it this way. Like dissolves like means a polar substance dissolves in a polar substance. Okay? And that's because the polar molecules are attracted to the other polar molecules of the other substance, whatever it is. So like, if they're both polar, they will dissolve in each other. Okay? Nonpolar dissolves in nonpolar. All right? So nonpolar dissolves in nonpolar. If they're both nonpolar, meaning they don't have positive and negative ends to the molecule, then they're going to mix more easily. But a polar and a nonpolar, polar and nonpolar, don't mix. Okay? So you've probably heard of oil and water, right? Not mixing. That's because water is polar, but oil is nonpolar. And as a result, they're not going to mix. They're not going to mix. Okay? We already talked about dissolving ionic compounds in water. That's what we mean by aqueous solution. Okay? Also, that's maybe called hydration, when the attraction of the charged ends of water molecules dissolve an ionic compound. Remember I mentioned this before? Basically, here we have an ionic compound, lithium chloride, and if you pull these apart, you're going to form lithium ion and chloride ions. Well, how do they get pulled apart? That's because if you put solid lithium chloride into water, the water here has a positive end. Here's a positive end of the water. It's going to be attracted to the negative ion of chloride. Here's the positive end of water, positive end of water. See how they're all kind of facing the same way towards this lithium ion? All the positive ends of the water are facing towards the negative lithium ion. But over here, this is, sorry, I said that I should say the negative chloride ion. I apologize, the negative chloride ion. Okay? Here, your positive lithium ion, all the negative sides of the water molecules are attracted to it. Okay? But they're going to get surrounded regardless because water's got a positive side that's going to get attracted to the negative ion, and it has a negative side that's going to get attracted to the positive ion. And they're going to pull them apart, meaning they're going to pull apart the lithium and the chlorine in order to make those ions. Okay? That's called hydration. All right. Another word that you should be aware of, if things don't mix, it's called, they're immiscible. Immiscible. Okay? The oil and water in the bottle are immiscible. They cannot dissolve into one another. If things are miscible, that means that they do dissolve. So you just have to be aware of those two terms. Okay? Remember, all you have to remember is like dissolves like. Polar dissolves in polar, nonpolar dissolves in nonpolar, but not polar and nonpolar together. Okay? Okay, now let's talk a little bit. We've been talking a lot about solids mixed in liquids. Let's talk a little bit about gas mixed in a liquid. Okay, let's talk about gases mixed in liquids, dissolved in a liquid. All right? Now, you are familiar with this because when you open up your soda can, your pop bottle or whatever you want to call it, right? Your carbonated beverage, you hear that release of that gas. That's because there is gas dissolved. It's under pressure, dissolved in that liquid. Okay? There is oxygen dissolved in water, in lakes and oceans, so that the life can the fish and other the fish would have to breathe that oxygen and take that out of the water. Okay, so they need that oxygen. So let's talk a little bit about gases mixed in a liquid, and there is an influence. There is a result of changing the pressure. Remember we talked about in a previous chapter about how pressure affects gases. Gases are like to expand, and you can add pressure to them, and as a result they can be compressed. Well, it's the same thing if they're dissolved in liquid. If you have a liquid, right, let's say that you've got your can of beverage here, and it has a certain liquid in there, and inside of that you have a gas dissolved in there. Okay, so you've got, I'm just going to put dots here to represent the gas particles. You actually wouldn't see them, but let's say those are gas particles in there. Okay, now those gas particles might want to escape, but if you put pressure on the top here, then those gas particles are going to stay dissolved. When you open up your beverage, the reason you hear that sound is because in the can, that liquid is under extreme pressure, and it's keeping the gas particles dissolved in the liquid. When you open it up, now the pressure above the liquid is the same as the atmospheric pressure. It's going to be less than in the can. And as a result, some of that gas is going to escape. So the less pressure you put on top of this dissolved gas in a liquid, the more gas that's going to come out. Okay? So gas and a solvent are normally in a state of equilibrium in which the gas molecules enter or leave the liquid phase at the same rate. There's that word equilibrium again. Okay? But if you change, if the pressure changes, is increased or decreased, okay, it's going to affect how much gas can be dissolved. In this case, if the pressure is increased on the gas, more gas molecules will stay dissolved. Okay, you'll be able to dissolve more gas particles. If you put more pressure here, you're going to be able to dissolve more gas in that liquid, or keep more gas even dissolved. All right. So that's why bottling companies are going to cause or force that gas to stay dissolved, or to dissolve it by putting them under pressure. Okay? So we have a formula that we can use that talks about how much gas is going to be dissolved in the liquid. It's called Henry's Law. It states that the solubility of a gas in a liquid is directly proportional to what? The pressure, the partial pressure of that gas above the liquid. Above the liquid. So here's your bottle again. Inside this liquid, you've got, right here, you've got carbon dioxide molecules, a gas, dissolved in the water. And you have carbon dioxide above. So the bottling company will force carbon dioxide in this space right here above the liquid so that these carbon dioxide particles are kind of putting pressure on the carbon dioxide dissolved particles and keeping them in the liquid. All right. Well, the second that you reduce that pressure, you open up this cap here. Now these CO2 particles that are in the gas phase above are going to go out, and you're going to reduce that pressure, and the gas particles that are mixed, are dissolved in the liquid, are going to turn into gas, and they're going to come out as well. And that's why you see all the fizzing and all the bubbling. Okay, they will not stay dissolved there in liquid if you reduce the pressure. Okay, so when you reduce that pressure, this causes the liquid to bubble and fizz, and is called effervescence. That's effervescence, is the bubbling action. Okay. All right. Yep. Okay. How about temperature on solubility? Now, we talked a little bit about this already, but what effect does temperature have on solubility? All right. An increase in temperature usually is going to decrease the solubility of a gas. Now, this is different than a solid. Listen carefully. Before I said this is for a solid. Okay, as temperature goes up, then the solubility would also go up. That's for a solid. If you increase the temperature, you're able to dissolve more sugar. But for a gas, it is exactly the opposite. Usually for a gas, if you increase the temperature of your water, your drink, if you increase the temperature, the solubility will go down. Okay? So again, here is something that you know. If you have a cold carbonated beverage, it's going to have more fizz in it. If you leave that carbonated beverage, even though the pressure around it doesn't change, if you leave it out and it warms up, you will start to see it release some of that gas, because it cannot hold on to it as easily. Those gas particles become, they gain more energy because they're getting heated up, temperature is increasing, and as a result, they're able to leave the dissolved state that they're in. Okay? So warmer beverages, we say they turn flat. A warm beverage loses that fizz, loses the gas that's dissolved in there. A colder beverage is going to be able to maintain and hold on to some of that gas that's dissolved in there. Also, colder ocean waters are able to dissolve more oxygen. They're rich with nutrients and oxygen, and that's why a lot of marine life go to colder waters in order to feed, or maybe to give birth. And so why? Because the water is richer with oxygen and nutrients, because it's able to dissolve more oxygen in that water if it's colder. Okay? So usually an increase in temperature increases the solubility of a solid. However, the effect can be more pronounced for some substance than other substance. Okay, but it's the opposite for gases. All right? Opposite for gases. Solids increase the temperature, solubility goes up. Gases, you increase the temperature, nope, solubility goes down. You cannot dissolve as much. Okay? So here we have, for example, solubility versus temperature for some gases. Here are some different gases, 3 of them. Notice, as temperature goes up, this curve goes down. It's an exponential decay, an exponential decrease there. Okay? So this particular gas, you can dissolve less and less of it. This is going down here. This is how much you can dissolve in grams. Oh, sorry, milliliters. It says milliliters of the gas in milliliters of water. So it's going to go down as the temperature increases. But for solids, look at these curves. They mostly go up. Most of them go up. There are a few that go down. Okay, there's an exception. There's kind of an exception a little bit maybe, but that probably is going up slightly. Okay. So, but for the most part, as temperature increases, solid solubility goes up. Okay? All right. We talked a little bit about enthalpy in a previous chapter, and we'll talk about it more later on, but when you create a solution, there is going to be an energy change. And the reason for that, remember I said that, like for table salt, when you put that into water, you have to pull, the water pulls them apart. Well, you can't just neglect energy if you're pulling something apart. It takes work to do that, okay? So a change in energy is going to accompany the formation of a solution. So either it's going to require energy to be put into the solution or energy is going to come out of the solution, okay? So for example, the formation of a solution is accompanied by an energy change. If I take potassium iodide and you put that into water, right? You will feel that container, let's say you put it in a glass beaker, it will feel cold. Why is that? Because heat is going from your fingers into the solution to help it dissolve that potassium iodide. Okay? So, here we go. Listen. Here's your solution. If you take potassium iodide, okay, there we go, potassium iodide, and you put it into water, you are making a solution. And as you do that, and your beaker here, if it feels cold, that means energy is going into it. Energy is going into the solution if it feels cold. Feels cold. There we go. Sorry. F-E-E-L. Feels cold. Energy is going into the solution to help dissolve that potassium iodide. This is called an endothermic process. Okay? Endo, it's entering. If energy comes out, if it feels warm to your fingertips, that means energy is coming out and going into your hand. And that's called an exothermic. Exothermic means it exits the system. Okay? The energy that is required the energy that is required to dissolve it, or the energy that is given off when it dissolves, is called the enthalpy of solution. Enthalpy of solution. Okay? The net amount of energy that is absorbed as heat by the solution when a specific amount of solute enters a solution is called enthalpy. Okay? Enthalpy of solution. In this case, they say absorbed as heat. I suppose heat could also be given off. All right? They give the example up here that when you put sodium hydroxide into water, it's going to feel hot. So that is energy is being released. So it is the amount of energy absorbed or released. Okay? All right. There's several things that have to happen when you make a solution, and this diagram shows us what happens here. All right? So let's say we've got this solid right here and this liquid right here. This is our solid and our liquid. And we're going to mix them together. This solid is going to be put into the liquid. All right? Well, step one, in order to make this solution, what has to happen is the solute, the liquid, in this case, the liquid particles, the liquid is a solvent. It's saying here the solute particles become separated from the solid. So basically what they're saying is parts of this solid here are going to get separated. You got parts of the solid that are going to get separated because it's interacting with the solvent that's in the liquid phase there. Okay, so solute particles become separated from solid particles. All right, all this is saying is that the solid starts to break apart. Okay, let's just make that statement. Solid breaks apart. In order to break something apart, you need energy. So here, energy is absorbed. Okay? Now, so this is showing you that energy is going into the system. Enthalpy is increasing. It's going in. All right? Now, also the liquid particles, the solvent particles, they have to be pulled apart as well to make room for the solid particle to come in. So those solvent particles, they get moved apart. Well, and again, anytime you move something apart that is normally attracted to each other, it requires energy. So more energies have to be put in. More energy has to be put in. But then what happens is you pull apart, let's say this is water, you pull apart the water, you pull up the liquid, you pull apart the solid, and now they begin to be attracted to each other. The liquid and the solid get attracted to each other. When they get attracted to each other, energy is released. So there could be a lot of energy released or a little energy released, and that's step 3 is the energy that is released once the liquid and the solid get attracted to each other. Okay? Once they're attracted to each other, then energy is released. So first step is the solid gets broken apart, then the liquid has to spread apart, then the solid and liquid come together, and energy is released. First step requires energy. You have to kind of heat it up a little bit. And second step requires you to heat it up as well. But the third step, when the solid and liquid then find each other and they're attracted to each other, then energy is released. So anytime things are pulled apart, energy is required, energy gets absorbed. Anytime that things are pulled together and attracted to each other, that means energy is going to be released. Okay? And the difference in how much it goes up and how much it goes down is going to give you the enthalpy of solution. Okay? If it goes down, look here, if it goes down more than the 2 steps going up, that means heat is released. Heat was released. Oops, released. If it goes down less, let's say this down arrow stopped right here. If it stopped right there, then the energy that went into the solution is less than the energy that came out. That would be heat, the total amount of heat was more. The heat absorbed was more, okay, than the heat is released, okay? So it's basically the difference in how much it goes up and how much it goes down to tell you, did it go down more? Was heat released? Was it exothermic? Or did it go up more than it went down? That means heat was absorbed overall, and that is endothermic. Okay? These are just specific values for enthalpy of the solution. You can look at those if you want. All right. All right, that concludes 12.2. And we're going to dive into here 12.3. We're going to be looking at an actual measurement that we can do to talk about how concentrated something is. How concentrated. So in your notes, put down concentration of solutions. Concentration of solutions for 12.3. Okay? So as we talk about concentration, you already are familiar with concentration. We say something is dilute if there's not a lot of the solute dissolved in the solvent, okay? A dilute solution has a relatively small amount of solute. So if you like your, I don't know, let's say lemonade, if you like it really sweet, you're going to dissolve a lot of sugar in there. It's going to be concentrated with sugar. And we might say that a concentrated solution is a solution that has a relatively high amount of sugar or solute, whatever the solute is, sugar dissolved in it. So that would be sweet. If it's not very sweet, you're not going to have very much sugar in there. Well, it's nice to say high amount or low amount, but we want actual numbers now. Right? Those are just relative. If I just say high, it's relative to something else. If I say low, well, it's low. All right? It's compared to something else. But we want actual number that we can calculate. And the two things that we're going to calculate to express concentration, those are molarity and molality. So here are two major things that you need to know. A and B, molarity and molality. What is molarity? Here we go. Molarity, our A here, is the moles of solute per liter of solution. It is expressed as this. Capital M is moles of the solute divided by liters of the solution. Okay? Liters of the solution. moles of the solute. So for example, if you're dissolving sugar in water, you'd have to find out how many moles of sugar do you have dissolved in the liters of water. Okay? Molarity is just one of the ways to express the concentration of a solution. All right? So if you see one capital M like this, it means you have a solution that is 1 molar. 1 molar is a concentration unit. A molar is a concentration unit. It means you've got 1 mole of something dissolved in a liter of the solvent. Okay? Let's look and see how we calculate this. Let's look at some examples, okay? So let's say that you had 40 grams, here's an example here. 40 grams of sodium hydroxide, okay? Well, 40 grams of sodium hydroxide, if you look on the periodic table and look at the molar mass of sodium and add it to the molar mass of oxygen and add it to the molar mass of hydrogen, you will end up getting 40. So 40 grams is 1 mole. So if you take 40 grams of sodium hydroxide and you put it into water, you have put in 1 mole of particles of sodium hydroxide. Okay? And if you have, so you put 40 grams into your water and then you add enough water to make exactly, the solution now is exactly 1 liter. Okay? What you would do to actually make this is you put in less than 1 liter and you dissolve all of your sodium hydroxide and then you make sure it's all dissolved, then you add more water in order to bring it up to exactly 1 liter because you want the solution after you've dissolved it to be 1 liter. Okay? You don't have 1 liter of water and then add the 40 grams because then it'll go higher. It'll increase the volume as you add something. It'll be more than a liter. So you want 1 liter of solution. So if you want 1 liter, now what you would have here, you put in a mole of sodium hydroxide and your total volume of the solution is 1 liter, your molarity would be 1 molar. So this is meaning you got 1 mole of sodium hydroxide in 1 liter of the solution. The entire solution has a volume now of 1 liter. Okay? So it is always the moles of solute over the liters of solution, the entire solution. Okay? Let's look at this example together. Let's say you have 3.5 liters of solution, and in that is 90 grams of sodium chloride. What is the molarity? Well, molarity is moles of the solute divided by liters of the solution. So we need to find moles of the solute. We're not given moles, we're given grams. You're given the mass of the solute, 90, and you're given the solution volume. You are given this bottom number here, 3.5 liters, but you're not given the numerator, you're given the mass, so we have to convert that to moles. So we're going to take the grams of sodium chloride and we're going to divide by the molar mass of sodium chloride. Okay? So right here, let's find the molar mass of sodium chloride. Well, and you look on the periodic table, sodium's molar mass is 22.99, chlorine, its molar mass is 35.45. You add them together, you get 58.44. Do we have 58.44? No, we've got 90. Well, this 58.44 is the mass of 1 mole. Well, we have more than 58.44. We've got 90. So we're going to take 90 and divide by 58.44. We have 1.54 moles of sodium chloride. Okay? Now you've got that top number. Okay? Now you've got this number here. So now you can take your 1.54 moles of sodium chloride and divide by the liters. There should be liters of solution here, the solution, not just the sodium chloride. And so now 1.54 divided by 3.5 gives us 0.440 molar. Again, what does that mean? 0.44 moles of sodium chloride per liter of solution. All right? You had 1.5 moles for 3.5 liters, so that is 0.44 moles for 1 liter. 1 liter. Okay? All right. Let's look at this example. Okay? This says to produce 40 grams of silver chromate, this guy right here, you need at least 23.4 grams of potassium chromate in solution as a reactant. All you have on hand is 5 liters of a 6 molar potassium chromate solution. What volume of solution is needed to give you 23.4 grams? Okay, so we need 23.4 grams. That's what we're looking for. All right. What do we have? We have a 6 molar solution, and we have 5 liters of it. So this is a hard problem. Just watch, and I'll walk you through it. Okay? We have the volume of the solution. We have the concentration of our solution. We have the mass of our solute. And I'm just going to stop right there. We'll get to the mass of the product in a second. Okay? We have that mass right there. What do we need? We need to know the volume of we need to find the volume in liters here. Okay? So remember molarity. Molarity is the moles over liters. Moles over liters. Okay? Now, in this problem here, what you actually are going to do is you're given this number. You're given this molarity right here. All right? And you're given this number right there. You're given the liters and the molarity. You should be able to find the moles that you have in those 5 liters. You have 5 liters of a 6 molar solution. So let's do that right now, okay? If I have, let's do this, 6 moles, and I have 5 liters. That means that the number of moles I have is what? I'm going to multiply both sides by 5, and this is going to cancel, and this is going to be liters here, and the liters in our units here are going to cancel. So I have 30 moles of this potassium chromate, okay? I have 30 moles of that. Well, I need to figure out, is that enough? I have 30 moles of that. Is that going to give me enough? Does that give me my 23.4 grams? Okay? I think it's going to give me more than that, obviously. Okay? I don't need all 5 liters of this. I only need a little bit of it because 30 moles is too much. Here, I need 23.4 grams of this, and let's find out what the molar mass of this guy is. Okay, so let's do this right here. The molar mass of potassium chromate, I have 2 potassiums, that's 2 times 39.10. I'm getting this 39.10 straight from the periodic table. Then I've got a chromium, that's 52 on the periodic table, and 4 oxygens, 4 times 16. That's a total of 194.2. Okay, 194.2. Well, if I need 23.4 grams, and 194.2 is a mole, if I take 23.4 divided by 194.2, I only need 0.12 moles. Well, up here, I'm not going to use all 5 liters because that gives me 30 moles. Okay? That's way too much. So I'm going to take my 1.2 moles, and I want to find what volume I need. Remember, molarity is moles over liters. Now I have the number of moles that I need, 1.20, okay? And my molarity is 6, and I want to find out what volume. So I'm solving for L here, liters. So liters is going to equal 0.12 divided by 6, which is what they're doing right here. And I only need 0.02 liters of that 5-liter solution. Okay? That's a hard problem. That's a difficult problem. It requires lots of different steps there. Okay? Okay. Our other measurement for concentration is molality. Molality. Molality is not going to be affected by temperature changes, which can change the volume, because you'll notice that volume is not in this calculation. It is, to find molality, which is going to be a small m, it always is, it still is, the moles of a solute, but it's divided by the mass of the solvent, not the mass of the solute, mass or solvent, not the mass of the solution, it's the mass of the solvent. Okay, so in our example of sugar water, you would find the moles of sugar, sugar moles, but you would divide by the mass in kilograms of, let's say, water. Just the water, not the entire solution, just the water. So it's moles of solute over mass of the solvent, and the mass is going to be in kilograms. Okay? Let's look at this example. So a solution was prepared by dissolving 17.1 grams of sucrose, there's our sugar, all right, in 125 grams of water. So it says find the molal, that's molality. Molality is moles over kilograms. So what are we given? We're given the mass of our solute. We have to change this to moles. And we're given the mass of the water. That's good. We want that, but it's given to us in grams. We have to change it to kilograms. Okay? Molality. Oh, we don't want molarity. We want molality. Molality. Okay? Molality is moles of solute over kilograms of solvent. So all we do is we have to find out what number of moles do we have. So we need the molar mass of this sucrose. We have 12 carbons, 22 hydrogens, 11 oxygens, for a total of 342.34. Well, we don't have 342 grams of this stuff. We only have 17. 17 divided by 342 tells us we have 0.05 moles. Small amount, 0.05 moles. Okay? And now we have the top number. We were given the bottom number, but we were given it in grams. So 12.5 grams, right? 125 grams, sorry, my fault. 125 grams, 1,000 grams in every kilogram. So I'm dividing by 1,000 and I get 0.125. 0.125. So you take your 0.05 moles divided by 0.125 and you get 0.4 molal for this sucrose. Okay? Again, that's a measurement of concentration, but this time in molality. Okay? All right, that is going to wrap up 12.3. I'll go over some more of these example problems in the chapter review questions. Okay? All right, so make sure you're taking good notes, and I will see you in the next video where I will go over the chapter 12 review questions. Okay? All right, great work. Let me know if you have any questions.